Hi, everyone. Welcome back from break. We're going to try to do these online courses. We'll see how it goes. So let's see. I've had to rearrange the homeworks because we didn't have class on Monday, obviously, and I'm not entirely sure how this is going to go over online teaching. So we can adjust the homeworks as necessary. Right now I have homework 4 due on April 4th, or April 3rd, sorry, that's a Friday. It's going to be turned in online. So I've made a place for you to turn in the homework online, and then we can grade it online and get it back to you. Turns out I'm not going to do live lectures. I said I was going to do live lectures over the over email before break. I'm not going to be able to do that because of scheduling. Having kids at home, not in school, means that I have to swap taking care of kids and trying to hold a schedule where I teach every day is not going to happen. So I'm going to record lectures up front and post them online. I will hold live office hours, and I will answer emails. And if that doesn't work, we will figure out how to make sure you feel like you're getting what you need from the course. So the office hours will be held at the normal times, Monday and Wednesday from 2 to 3:30, and that's going to be done via discussions on Canvas. I will provide directions on how to get to join the discussion. I'll post a number of announcements so that everyone will be up to speed on what the plan is. Let's see, we will get your test back to you, or at least graded, hopefully by the end of this week. Yeah, so let me know if you have any questions before or whenever. If not, I will be posting these lectures and holding office hours, so you can log in and tell me then, or over email. So let's get started with lecture 6. We left off on we finished up lecture 5 before the break. We were doing regression with single regressors, and we were doing confidence intervals and t-statistics for the and p-values for the coefficients beta 0 and beta 1. Now we're moving to linear regression with multiple regressors. So this is lecture 6. The notes are online. What you should see on your screen here is a whiteboard. I'll be writing on this whiteboard. Hopefully I can get used to this, and so can you, and the writing is not too bad. We're going to start with omitted variable bias, or basically why would we care about adding multiple regressors or multiple x variables? So let's start with a student-teacher ratio example. And we're going to have, like we normally had, test scores. So we'll have test score for person I, or for not a person, but a school district, as a function of student-teacher ratios in that school district with an error term. So there's our basic test score as a function of student-teacher ratios regression. But regressing test scores on just student-teacher ratios leaves out some important information, important determinants of test scores. That was what we were talking about with R-squareds. R-squareds were what's the percentage of the variation in Y, or test scores in this case, that's explained by student-teacher ratios? Well, probably not very much. There's probably a lot of left out information. And the left out information is collected or contained in this error term, U. So all that leftover information is contained in the error term U. What could be in there? Could be school characteristics like teacher quality, or computer usage, or things like that. It could be student parent characteristics like family background and average income in the school district. We've had some of these examples in class before. The example the textbook gives is the prevalence of non-English speaking students, or essentially the percentage of English as a second language students. So students that speak a different language as their first language at home. The percentage of those students in each classroom or in each district. The reason this is a problem is because if we ignore these additional variables, or we ignore the information contained in U, then we could end up with biased estimates of beta 1 hat. So biased estimates of beta 1 hat here. Let me blow that up a little bit. Bear with me as I get used to using these electronic resources. So why could we end up with a biased estimate of beta 1 hat if we don't account for this information? So let's consider students that are also learning English while they're learning other subjects like math and so forth. So if a student is learning English, they're likely to perform poorly on a math test. So if the test scores in this equation is a math test score, then the students that are also learning English at the same time are likely to perform less well than the students that already know English, or the ones that are English first language speakers. So that means that U is going to be negatively correlated if you're a district with higher percentage of students that are learning English, or students with English as a second language. That's going to be negatively correlated with test scores. So that's going to negatively bias our beta 1 hat estimate. This would be called a spurious relationship between student-teacher ratios and test scores. In fact, it's potentially not actually the relationship between student-teacher ratios and test scores. It's instead the relationship between percent English as a second language students and test scores. We also need class sizes to be correlated with test scores for this to happen. Or class sizes, student-teacher ratios to be correlated with the percentage of English as a second language students. So let's write out this relationship. So pretend we have here. Let's draw this box. We have test scores here. We have class sizes over here. This is going to be the relationship that we are trying to estimate is this. So student-teacher ratios affect test scores. This is what we're estimating. We think that the causality goes that direction, that student-teacher ratios are affecting test scores. So this is what we are estimating. But we also have an error term, And what's contained in the error term, we're going to assume for the moment that the only thing contained in there is the percent of English as a second language students, percent ESL. So this is ESL captured, whoops, that should say captured in UI. Percent ESL captured in UI. I should have put a hat up on here because I put hats on the betas. All right, so we're trying to estimate the relationship between student-teacher ratios and test scores, but turns out there's correlation between student-teacher ratios and the percent ESL. It could be the case that higher percentages of ESL students is positively correlated with class sizes. So poorer school districts might also have higher percentages of students of ESL students, and they probably also have higher class sizes. It's not a causal relationship. It's not as though higher percentages of ESL students result in it's not as though higher percentages of ESL students result in larger class sizes. It's just a correlation. It's actually probably coming from lower incomes in the school district. So there's a correlation here. So we have arrows on both sides, arrows here and arrows here. Arrows on both sides indicating that there's a correlation. Arrow on one side up at the top between student-teacher ratios and test scores indicates causation. We're going to assume that the correlation here is positive, that higher percent ESL is positively correlated with student-teacher ratios or class sizes. Now, we also know that students that are ESL students probably are going to perform worse on tests. It's not because they're less intelligent, it's just because they're simultaneously learning English, which makes it harder. So we're going to have some negative correlation here. So the correlation over here is negative. That should be, I'm going to use my eraser here, fix that up. Correlation here is negative. So we have negative correlation. All right, I get to use different colors now. Negative correlation between percent ESL and test scores, and positive correlation between student-teacher ratios and the percent of ESL students in the classroom. What is this going to lead to? Well, if we multiply a negative by a positive, that's a negative bias. So this little diagram can help us figure out the direction of bias in our estimates. And what's biased? Well, this bias, the bias we're talking about, these two things, let me draw it like this, are going to affect our estimates of beta hat 1. So in this case, because we have a negative multiplied by a positive, we're going to get negative bias in our beta hat 1 estimates. So that means that our population coefficient, beta 1, we're trying to recover that with our regression. And in our estimate, when we leave out important information, or when UI contains important information like percent ESL, we're going to get biased estimates of beta 1. And we're not going to recover the population estimate beta 1. We're going to recover something that's less than that because we have negative bias. So when we estimate our model, beta hat 1 is going to be less than the true population parameter. Can we test for this? Is there a way to determine if we have a bias coefficient? Well, not really. We can look at, we can't say for certain because we'll never know the true population parameter, but we can make arguments, and we can also look for, correlation. We can do some things to kind of make arguments that we do have unbiased or biased coefficient estimates. And this is primarily what econometrics is about going forward, is trying to determine if we have, or make arguments that we have, unbiased coefficient estimates, or we have coefficient estimates that actually mean something. So how can we test for this? So if we have data on percent ESL, we can test. So suppose we know we have data on test scores and we have data on student-teacher ratios. We can also test if there's correlation between percent ESL and student-teacher ratios. So we can test. Yeah, let's write in blue. So we want to know, does this relationship hold? The one in blue here. Is there a correlation between percent ESL and student-teacher ratios? If there's not, then we don't have to worry. But if there is, then we would have to worry. So we can test for correlation between percent ESL and student-teacher ratios. We can just estimate the correlation. If it turns out that when we estimate the correlation, if it equals 0, then we don't have a problem. But if it turns out that the correlation does not equal 0, then we do have a problem. We know we have omitted variable bias in this regression up here. So if we collect data on the percent of ESL students in the district, and we find that there's correlation between percent ESL and student-teacher ratio, we know we have omitted variable bias. All right, so that leads to omitted variable bias. That's the key term for this section. Omitted variable bias. So there's two conditions for omitted variable bias. And this omitted variable bias, I'm going to call it OVB, omitted variable bias. There's two conditions for this. And this is really the motivation for multiple regressors. There's two conditions for omitted variable bias to exist. First we need the omitted variable. The omitted variable, the thing that's contained in U, is correlated with the included regressor. Okay, what does that mean? The omitted variable is included with the regressor. So the variable contained in U, the one we're concerned about, in this case percent ESL, has to be correlated with student-teacher ratios, the included regressor. Or in other words, something in UI is correlated with XI. So something in UI is correlated with XI. That's condition number one. So if either of these conditions hold, the two conditions, then we don't have omitted variable bias. If they do hold, so that's the key. If they don't hold, if either one of them does not hold, then we don't have omitted variable bias. But if they do hold, then we will have omitted variable bias. So the second condition is the omitted regressor, or the omitted variable. The omitted variable is a determinant of the dependent variable. Every time I lift my hand up, this thing moves. I have to get used to this. So there we are. The omitted variable is a determinant of the dependent variable. Let me erase this sort of nonsense here. Sorry about that. The omitted variable is a determinant of the dependent variable. My handwriting was very bad on the whiteboard, and now it's even worse. Hopefully, it doesn't hinder your learning. But I'm copying almost directly from the notes, so you can read off those. This is something in UI determines YI. Okay, something in UI determines YI. In other words, we could write this as, it doesn't have to be determining it in the sense that it's causing it, but we know that what this really means is that there's correlation between UI and, well, UI and Y. There's always going to be correlation between UI and Y, but the something in there is that we're forgetting is determining YI. So in this case, percent ESL, in our example from above, percent ESL is contained or captured in UI. We know that it's a determinant of test scores. We know that the percent ESL influences the average test score. We also know, or we're going to make the case that the percent ESL is correlated with student-teacher ratios. That's condition number 2 up here. Something in UI is correlated with XI. Something in this case is percent ESL, something in UI, and we're making the case that it's correlated with XI. We're making the case that up here, higher percentages of percent ESL, higher percentages of ESL students is positively correlated with class sizes. So class sizes are larger when they have higher percentages of ESL students. Okay, so this is a key concept, omitted variable bias. Why does it matter? Okay, well, we know it matters because it biases our coefficient estimates, but it also, we can write it in terms of our assumptions for OLS, ordinary least squares. What were our assumptions before? Assumption number 1, OLS assumption 1, the modified OLS assumption number 1, after we looked at the Gauss-Markov theorem, was like this. It's like this. The expected value of u conditional on x equals 0, meaning that our error term conditional on x was equal to 0, which really implied that the correlation between u and x was equal to 0. So that's OLS assumption number 1. Okay. Now, what did we just say in the previous example up here? So what did we just say? Well, it's hard to see. We said that, in fact, something contained in UI was correlated with student-teacher ratios. So that violates this. That violates our OLS assumption number 1. So the Gauss-Markov theorem doesn't hold. That means we have bias coefficients, and we aren't estimating the most efficient estimator of beta hat 1. That means that when all of our assumptions don't hold, it's particularly assumption number 1, the OLS estimator is biased. My goodness. OLS estimator is biased and inconsistent. So we had biased. Unbiased was our condition, our Gauss-Markov theorem. Said if all of the assumptions hold, then we have unbiased estimates. And it's inconsistent. And what does that mean? That means that even with large samples of data, our bias does not disappear. So why is that important? Why would we care? Why do we want unbiased estimates of our coefficients? Well, hopefully it's obvious. We're using statistics and econometrics to estimate relationships that can help us make decisions. So if you're using this to determine, if you're hired by a school district to determine should you invest resources in reducing class sizes, and you estimate these models, and you get a biased coefficient estimate, then you can't really make informed policy decisions. Another example, suppose you're using regression to determine how much more yield you get if you apply fertilizer to crops. If you apply the fertilizer in a non-random way, like we talked about prior to break, if we don't have a randomized controlled experiment and we're applying fertilizer based on some systematic criterion, like the crop was doing poorly last year, then we could get biased estimates of our coefficients, of our regression of crop fertilizer and our crop yields regressed on fertilizer. And then we could determine that fertilizer actually doesn't impact crop yields or something similar like to that. Another example, we could be trying to figure out how we could be running a clinical drug trial. And suppose a pharmaceutical company is trying to introduce a new drug. And suppose OLS says that the drug helps people get better. A perfect example right now is there's a lot of false information coming out about vitamins and things you can take to help you not get the coronavirus. So maybe that's just false information, but maybe somebody actually believes that's true. And why might they believe that's true? So suppose somebody got data that said, okay, these people take vitamins and they also did not get the coronavirus. Well, what if the people that took the vitamins are also the healthiest people? And we're not really getting tests for coronavirus right now. So we don't really know if people are getting coronavirus, and those people, maybe it's only young, healthy people that are taking vitamins. And those young, healthy people, they might actually have the coronavirus, but their symptoms are so mild that they don't even notice. And so it looks as though, if you run this regression with the data, it looks as though people that take vitamins aren't getting the coronavirus, but in fact, we have a bias, or we have a non-random sample of people taking vitamins. It's the people that are healthiest and youngest taking vitamins, but they're also the ones that are most likely to not get the virus, or the ones that are most likely to not show symptoms when they get the virus. So we're going to get bias estimates of our effective vitamins on getting the coronavirus, and that's not good, because then we're going to, if somebody believes that regression, then they could go out and say to the public that you should take vitamins, and then there'll be a rush on vitamins. People will go to the stores to buy vitamins and cause the price of vitamins to go up. But more importantly, people are going to run to the stores to get vitamins and infect each other with coronavirus in the hopes that eating vitamins is going to stave off getting a coronavirus, but it's actually not. They're actually just doing damage. So we care about omitted variable bias. We care about bias coefficient estimates. We actually have a formula. We have a formula for omitted variable bias. Formula for omitted variable bias. The formula looks like this. When when the Gauss Markov assumptions hold, or when our OLS assumptions hold, and we have an unbiased coefficient estimate, we're all good. But when they don't hold, in particular when assumption number 1 holds and we have omitted variable bias, we end up with beta hat 1 converges. This little arrow means converges, and that means when the sample size gets large, it converges to beta 1. Okay, so without omitted variable bias, beta hat 1 converges to beta 1, the true population parameter beta 1, the true slope. But when we have omitted variable bias, we have to add on an additional thing here, this term here. So that's a rho. That little p should look like a rho. So if you look up your Greek letters, that's rho. It means the correlation between x and u, so that we wrote that up above. It's the correlation between the included regressor and the error term. And we also need the standard deviation of the error term over the standard deviation of x. Okay, so this says that when we have omitted variable bias, our estimate of beta hat 1 converges to, when the sample size gets large, it converges to beta 1 plus some additional thing. And that additional thing is a function of the correlation between x and u. So that bit there. So if the correlation of x and u, equals 0, then this whole term here goes away. This whole term here goes away, and we're left with an unbiased estimate of beta hat 1, or it converges in probability to beta 1. But when this does not, when the correlation between x and u does not equal 0, then we have to consider this extra term here. And so that's why we looked at this. We looked at this formula, or this diagram up here. We were thinking about, is the correlation between x and u positive? Let's use green now. Is this correlation positive or is it negative? Well, now we can look at how negative and positive correlation affects our bias. If the correlation between x and u, this term here, is positive, then beta hat 1 converges to beta 1 plus something, because the standard deviations, these terms here, standard deviations are always positive. So the direction of bias is directly dependent on the correlation between x and u. If the correlation is positive, then beta hat 1 converges to beta 1 plus something. If the correlation is negative, then beta hat 1 converges to beta 1 minus something. Also, another thing to think about here, so not only can we sign, not only can we sign the direction of bias if we have this correlation, we can also determine the magnitude of bias if we can determine the magnitude of the correlation. So as the correlation increases and the standard deviations of the errors and the x's increase, then the bias is going to increase. Okay, so there's 3 ways to overcome omitted variable bias. We know it's a problem. 3 ways to overcome omitted variable bias. We know it's a problem. We have to do something about it. The first is something we've talked about before. The first is run a randomized controlled experiment, in this case with a student-teacher ratio and percent ESL and test score example. We would randomly assign student-teacher ratios, and then ESL would still be a determinant of test scores, but ESL would be uncorrelated with student-teacher ratios. Let's think about that logically. So if we had, in reality, class sizes are not randomly assigned. class sizes are dependent on the school district, the resources within the school district. Poorer school districts are going to have higher class or larger class sizes. But if we were able to randomly assign class sizes, then the random assignment would ensure that the class size is not correlated with percent ESL. Just like we had with the farming plots and fertilizer yield, we want to randomly assign fertilizer to plots. In that way, the fertilizer application is not correlated with the productivity of the plot. But that's not usually realistic in practice. We don't have the ability to randomly assign class sizes, and we typically don't have the ability to randomly assign our treatment or our X variable. Unfortunately, we would like that. That's kind of the gold standard in statistics, but we're econometricians and we use observational data. So number one, 3 ways to overcome omitted variable bias. Number one, we have a randomized controlled trial. We don't usually have that, so let's move to number 2. I don't like that. Let's get rid of that. Number 2. What's number 2? Okay, suppose that our only variable that we're concerned about can be contained in U is percent ESL. So we could cut up the data. We could say, all right, we have high ESL, high percent ESL school districts, and low percent ESL school districts. Excuse me. We could cut up the data into a high percent ESL and low percent ESL segments. So that would mean that we could look at the relationship between student-teacher ratios and test scores within these groups. So if we have a high percent ESL group, then we could find the relationship between class size and test scores for the high percent ESL group, and then we could find the relationship between class size and test scores for the low percent ESL group. So we would have 2 separate regressions on 2 data sets, and assuming there's only that percent ESL can be cut up in this meaningful way between high and low, then we could remove that correlation between percent ESL and student-teacher ratios. That's not the greatest because we're cutting up our data, so we're losing statistical power. We know that our beta hat 1 estimates, our standard errors, depend on the sample size. So if we cut up our data, our sample size gets cut in half essentially for each regression, the high and low percent ESL regressions. And so we're going to lose statistical power, which isn't good. We don't really want to do that. The third way to do it, if we have data on these omitted variables, is to include them in the regression. So the third way, if we think that percent ESL is an omitted variable that's causing problems, the third way to deal with this is include percent ESL as an additional regressor in multiple. So this is called multiple regression. So what we've done so far is single variable regression. Now we're doing multiple variable regression, So if we have the data on these variables, we might as well include them in the model. So what that leads us to multiple regression models. Let's go with blue for this. Let's introduce the multiple regression model. Multiple regression model. Here's the general setup. So before we had yi equals beta 0 plus beta 1 xi. That was our original regression plus an error term. Now we need to add a 1 on this xi because we're going to have 2 or more included regressors. Promised we were going to do this before break. Beta 2 x, let's do x2i plus ui. So we could have more than 2 x's. In this case, we're going to start with 2. Y is still the dependent variable. Now we have x1i and x2i are 2 independent regressors. So y is still the dependent variable. That hasn't changed. X1 is the same as it was before, but now we're adding x2 as a second independent variable or independent regressor. Beta 0 is the intercept, same as before. So if we set x1 and x2 equal to 0, now we have the intercept, which is the average value of y when x1 and x2 equals 0. The unknown population intercept, beta 1 equals the effect of, or the effect, let me do effect on yi of a change in x1i holding, here's the key difference, holding x2i constant. Okay, so that's different than our single regression model. That should, let me move that over so you can see that. That's different than our single regression model, where beta 1 is just the effect on y of a change in x1. Now we have beta 1 equals the effect on y of a change in x1i holding x2i constant. So we're holding, in this case, percent ESL constant if x2i is percent ESL, or we're controlling for x2i. Likewise, beta 2 is equal to the effect on yi of a change in x2i holding x1i constant. And ui equals population ui is equal to the population error term. Same as before. Okay, can we provide a little more interpretation of these coefficients? Let's see. So beta 1 equals, we can also write this as the change in y over the change in x1 holding x2 constant. Or if you've taken calculus, beta 1 is equal to the derivative. Well, let's use, if you've taken partial derivatives, you know that this is equal to dy the partial derivative of y with respect to x1. So we're going to hold x2 constant and take the derivative of this function up here. Take the derivative of this with respect to x1 holding x2 constant. That's essentially the interpretation, the slope. Beta 2 is just going to be equal to beta 2 is going to be equal to the change in y over the change in x2 holding x1 constant, or dy dx2. And beta 0, let's just make sure we have this. Beta 0 is predicted value of y when x1i equals x2i. X2i equals 0. Okay, the predicted value of y when x1i equals x2i equals 0, or y bar when x1i equals x2i equals 0. Okay, so we're still estimating beta 1 hat and beta 2, well, beta 0 hat, beta 1 hat, and beta 2 hat using ordinary least squares. So that doesn't change. Let's just make sure we have the formula for that. So OLS estimator with one regressor was, we had OLS estimator with one regressor is minimizing, well, yeah, one regressor gives us a beta hat 0 and a beta hat 1. We're going to minimize, making a mess of this. We're going to minimize our function, which was the sum of I equals 1 to n of the u hat I squared. And we can plug in the definition of u hat I. So this thing is going to be equal to min over these two variables, beta hat 0 and beta hat 1, of the sum of I equals 1 to n of yi minus the predicted values of y. Now we know that we can plug in the definition of y hat, the predicted values. Those predicted values are going to be our coefficient estimates multiplied by, forgot the squared up here. There we go. So now we know, we can see that our coefficients enter this here, enter this setup here. That's OLS, ordinary least squares for one regressor. Now let's do it for two regressors. OLS for two regressors. Doesn't really change much, but let's just make sure we know what it is. Okay, so we can start with, we know it's the same as this up here, what I'm circling. Now let's plug in the, we're actually going to minimize now over beta hat 0, beta hat 1, and beta hat 2. But we're going to minimize the same thing. I equals 1 to n, all of our observations. Apologize for the sloppiness here. I'm trying to write this as neat as possible. Now we can substitute in for the U hat up there. Can substitute in. So we still have yi minus the predicted values of y hat I. Now let's just plug in I need some commas. There we go. Now let's plug in the definition of y hat I. So y hat I now is equal to this. There we go. So it looks a little different in that we now have a second regressor here that we've added. That's the only difference. So we're still estimating ordinary least squares, but we're now minimizing a function over 3 unknown parameters, beta hat 0, beta hat 1, and beta hat 2, whereas before we were minimizing over just 2 unknown parameters, beta hat 0 and beta hat 1. So that means we're going to have, in this case, 3 degrees of freedom. We had 2 degrees of freedom before, 3 degrees of freedom, y3, because we have 3 parameters, beta hat 0, beta hat 1, and beta hat 2. And so that 3 degrees of freedom will enter into your standard error estimates, but don't worry, statistical packages will do that for you. You don't have to manually adjust that. Okay, I think I'll stop there for this first lesson and or for this first lecture or class, whatever we're going to call them. And I'll post a second one in a little bit.